Eriez Magnetics, world authority in advanced technology for magnetic, vibratory, and metal detection applications. Eriez presents Magnets in Everyday Life. Magnets are in use in practically every facet of our daily lives, from tiny magnets that drive cell phones, speakers, and computers to larger ones for commercial applications. We use magnets every day. Let's take a look at the definition of a magnet. It is an object that produces a magnetic field, either natural or induced, that attracts ferrous materials.
Some people have an unusual amount of natural magnetism. We invited this fellow over for dinner. He left with all me mom's silverware.
Greek folklore tells of a shepherd named Magnes that discovered Lodestone on Mount Ida around 2500 BC. It is said that the nails in his sandals and metal-tipped staff stuck to the rocks as he climbed up the mountain. All iron ores have magnetic properties. Magnetite is an iron ore that exhibits a strong magnetic signature and found in many igneous and metamorphic rock. Lodestone is magnetite with a specific crystalline structure that had a strong magnetic field applied. Lodestone may be created in nature by lightning striking a deposit of magnetite. Lodestone is a natural permanent magnet. The Chinese used the name loving stone to describe the attractive nature of lodestone. The first use of crude compasses were recorded in China 3,500 years ago. Cleopatra believed that sleeping on lodestone kept her skin youthful. Like poles repel, opposite poles attract. Magnetic lines of force flow from north to south outside the magnet, and from south to north inside the magnet. Magnetic fields are stronger at the poles. Magnetic lines of force form complete loops. They never cross. This video shows how like poles repel each other. The aurora borealis and the aurora australis are created when solar winds collide with the magnetosphere.
With spring right around the corner, it's the season for auroras. Also known as the northern lights, auroras are the brilliant curtains of colored light that appear in the night sky in the far northern or southern regions of the world. Although auroras are spectacular to watch, they're actually a manifestation of violent space weather.
These are just caused by energy coming into our Earth's magnetic atmosphere, causing the whole magnetic field to reconfigure and end up with an explosive release of high-energy electrons and protons into our Earth's atmosphere, where they strike the molecules, both oxygen and nitrogen, and cause them to glow.
Besides igniting the northern lights, these substorms can create big problems here on Earth by disrupting power grids, satellites, air travel, and even GPS signals. Spring is one of the best times to view the auroras, because the substorms that spark them are more frequent in the months around the equinoxes. Plus, the longer nights provide a great backdrop for these stunning displays. While auroras have fascinated observers for centuries, little had been known about their origin. But NASA's aiming to resolve this mystery with a new mission to study the northern lights called Themis. The Themis mission uses 5 identical satellites and a network of ground observatories to track and determine what triggers the auroras that occur during substorms. And since its launch just last year, Themis has made some important discoveries.
Even in the first days of our mission, we've used the 5 spacecraft and the dedicated array of ground observatories to track aurora racing westward across Canada and Alaska and time their motion and understand where they occur.
As our knowledge about the northern lights continues to expand, pretty soon, auroras may not seem so mysterious after all.
Igor, let's give him a magnetic personality.
Yes, Master. He'll get a charge out of that.
Atoms have a nucleus of protons and neutrons surrounded by a much larger cloud of electrons. Magnetic moments happen when neighboring atoms have electrons facing the same way. Atoms possessing these magnetic characteristics group into regions called domains. A domain is the smallest known permanent magnet. 6,000 domains would occupy an area the size of a pinhead. Unmagnetized ferromagnetic materials have domains that are randomly oriented and neutralize each other. Ferromagnetic, material that is strongly attracted to magnets. Paramagnetic, material that is weakly attracted to magnetic fields. This represents most materials. Diamagnetic, materials that are repelled by magnetic fields. Examples of living magnetism include certain birds, butterflies, and insects which seem to have small amounts of magnetite in their head and body. Monarch butterflies use magnetic cues in the environment to assist in migrating over 2,500 miles each year to breeding grounds in Mexico. The oldest naturally occurring permanent magnet is lodestone. Ceramic magnets are composed of iron and barium or strontium oxides to create permanent magnets. Ceramic magnets can store stronger magnetic fields than iron itself. Alnico alloys make strong permanent magnets and can be magnetized to produce strong magnetic field strengths at their poles, as high as 1,500 Gauss. Alnico magnets are the oldest man-made permanent magnets still in use. Unmagnetized ferromagnetic materials may become magnetized by applying a magnetic field or electrical charge. Ferromagnetic materials can be demagnetized by reversing the polarity. Softer materials, such as iron, require less external magnetic force to magnetize. Harder materials, such as alnico, require a greater external field that will produce a much stronger magnet. Rare earth magnets are strong, permanent magnets made from alloys of rare earth elements. Rare earth magnets are substantially stronger than ferrite or alnico magnets. Neodymium magnets are the strongest and most affordable type of rare earth magnet. Neodymium magnets are made of neodymium, iron, and boron and are typically used in most computer hard drives and a variety of audio speakers. This demonstration shows the strength comparison between ceramic and rare earth magnets of equal size. The ceramic and rare earth magnets will easily pick up steel hex nuts. The ceramic magnet does not contain enough magnetic strength to lift the 12-pound block of steel, but the rare earth magnet has no trouble. Samarium cobalt magnets are less common than neodymium magnets because they are more expensive to produce and create a weaker magnetic field. Samarium cobalt magnets have a relatively high Curie point, which makes them suitable for high-temperature environments. The Curie point of a ferromagnetic material is the temperature above which it loses its magnetic ability. All magnets lose their strength when heated. Alnico magnets work very well at high temperatures. Injection molded magnets are a composite of resins mixed with magnetic powder. This allows complex shapes to be formed. Samarium cobalt magnets are highly resistant to oxidation. They also possess a higher magnetic strength than alnico or ceramic materials. Magnetic fields have been shown to promote plant growth. Here is an image showing how iron filings concentrate on the flux lines of a magnetic field. Magnets are measured with Gauss meters, magnetometers, or pull test devices. Gauss meters measure the strength in CGS units of magnetic induction. Magnetometers measure the strength and/or direction of the magnetic field. Pull test devices measure the amount of force needed to release an object from a magnetic surface. Here are some examples of Gauss measurements. Gauss measures the intensity of magnetic field lines per square centimeter. The Earth's Gauss has approximately 1 magnetic field line per square centimeter. Magnetic Gauss strength drops considerably only inches from the source. Magnetic shielding, or more precisely shunting, is a way of redirecting a magnetic field through a permeable material. Permeable materials are attracted to magnets. The shunt allows the magnetic field to travel from the magnet's north pole to its south pole through the material. The shunt will not completely shield against all magnetic flux. It will only limit it. A Faraday cage or Faraday shield can block out external static electric fields to protect electronic equipment. Microwave oven housings are a type of Faraday cage. A steel C-frame connecting the north and south poles of a rare earth magnet will shunt, or redirect most of the magnetic flux lines through the steel. Nikola Tesla was an inventor, physicist, mechanical engineer, and electrical engineer. He was best known for his contributions in electricity and magnetism. Tesla's theoretical work led to the basis of modern alternating current, or AC, electric power. Named in his honor, the Tesla is a measurement of magnetic flux density, or magnetic induction, and is used for stronger Gauss measurements. 1 Tesla equals 10,000 Gauss. The Earth's poles make up our largest terrestrial permanent magnet. The Earth's north pole is actually the south magnetic pole. The Earth's magnetic field is created by molten iron circulating in the Earth. The magnetic field has weakened 10% since the early 1900s. Geological studies of magnetite show that the Earth's poles have exchanged places 171 times in 71 million years. Although uncertain, the change in polarity could take thousands of years. This is a simulation of how the fields would act during a reversal of magnetic poles. Ancient civilizations believed that magnets held special powers of healing. Magnets have been used in health-related treatments since the earliest magnet discoveries. Magnet therapies are still in development today. Early medical treatments used magnets like this 800-pound electromagnet, which was used to remove steel cinders from patients' eyes. Testing equipment, medical monitors, pumps, switches, motors, speakers, and more rely on magnets. Magnetic imaging looks into the human body. Industrial magnets are utilized in lifting, conveying, and recycling. Magnetic grates, plates, and traps remove contaminants from products. Food, pharmaceutical, cosmetic, manufacturing, and mining industries are just some of the fields that use magnets daily to ensure quality. Lift magnets are constructed to lift many times their own weight. Magnets are used to convey materials from one process to another. Bar magnets pulled along by chain drives or linear induction motor feeders are just two of the ways that magnets help to get the job done. A linear induction motor is essentially a multi-phased alternating current electric motor that has had its stator unrolled so that instead of producing a torque or rotation, it produces a linear force along its length. Linear induction motors are used in many commercial and recreational applications. Maglev trains also use this technology. Magnetic separators remove ferrous metals from contaminated products. Eddy currents are created using a special permanent magnetic circuit to repel non-ferrous metals during separation. Eddy currents are swirls of magnetic repulsion caused when a conductive metal, such as aluminum or copper, intersect a strong alternating magnetic field. Eddy currents can be used as a magnetic brake by creating a field around a spinning non-ferrous disk. A circuit can be created to harness the eddy currents and return them back to a battery as an electric charge. Here is a demonstration showing the effect of a strong magnetic field against a conductive material like aluminum, creating eddy currents. The stainless steel rolls easily through the aluminum channel. The rare earth magnet's strong magnetic field acts as a brake against the conductive aluminum. Powerful electromagnets are suspended over a flow of material. Contaminants are pulled up as they pass under the electromagnet. A moving belt discharges the ferrous materials out of the flow. A simple electromagnet can be made by wrapping an insulated wire around a nail and connecting the two ends of the wire to a battery. A suspended electromagnet is a much larger version of that concept. When current passes through a conductor, it creates a magnetic field. The image on the left shows a magnetic field for current flowing through one wire. The image on the right has current flowing in opposite directions. These wires repel each other.
These are some of the pioneers of magnetism. André Marie Ampère is credited for creating the International System of Units, or SI. The ampere, or amp, is a unit of electric current, or amount of electric charge per second. Johann Carl Friedrich Gauss developed a way of measuring magnetism in terms of mass, length, and time. Hans Christian Ørsted discovered the relationship between electricity and magnetism known as electromagnetism. Michael Faraday is noted for significant contributions to electromagnetism and electrochemistry. Joseph Henry discovered electromagnetic phenomenon of self-inductance. The relay for the telegraph came from this discovery. Heinrich Friedrich Emil Lenz, Lenz's law is an electromagnetic theory for determining the direction of flow of induced currents. Wilhelm Edward Weber created a system of absolute measurements for electric currents. James Clerk Maxwell described the interrelationship between electric fields, magnetic fields, electric charge, and electric current. Nikola Tesla, patents and theories led to modern alternating current, or AC, and polyphase power distribution. Many other inventions and discoveries have led to advancement of many modern daily conveniences such as radios and computers. Pierre Curie, pioneer in crystallography, magnetism, piezoelectricity, and radioactivity. Eric Roberts Lathwaite developed the linear induction motor and maglev train system.
Magnets will continue to play an important role in your everyday life. Take some time to investigate magnets and their varied uses. Look into the life and careers of the pioneers that helped us understand magnets as we know them today. Research careers involving magnets. We invite you to further explore the history, mystery, and magic of how magnets are used in your everyday life. We hope you enjoyed this educational program brought to you by Eriez.